In this lecture we talk about primitive element theorem. So say we are given a finite extension E over F, and E is obtained by adjoining say A1, A2 all the way to AR to F. And A2 to AR, these are separable over F. So notice that we are not talking about A1. So A1 may not be separable. So then there exists gamma in E. So there is some element gamma in E such that you can rewrite E as gamma adjoint to F. So that is, you can forget about all these elements and just replace them by a single element. So that is why it is called primitive element theorem. So you are replacing a number of such elements with a single element. So the proof is divided into two parts. The first part is the finite field. So consider a finite extension E of a finite field F. So your base field F is finite. If you have a finite extension, then E will also be finite. Now since E is finite, you consider its multiplicative group. So that is, you drop 0 out of E. You have E cross, which is just the multiplicative group, which is without 0. So this multiplicative group is finite precisely because E itself is finite, and therefore it is cyclic and generated by a single element gamma. So since this multiplicative group is just generated by a single element gamma, and 0 is obviously there in F, so you can just obtain E by adjoining gamma to F because multiplicative group is generated by gamma. So this theorem that multiplicative group is finite and therefore is cyclic. So this is a big result. The multiplicative group which is finite implies that it is cyclic. This you can find on page 315 of Dummett and Foote, second edition. So this is proposition 18. So that is what we are using. Now we come to infinite field F. So for infinite field we need to prove for r equals to 2. So you start like this. Then if the theorem is true, then you can adjoin these two elements and adjoin them into G1. So this becomes G1 A3 to AR. Then you can adjoin these two. You get G2. Then G2 comma A4, A5 all the way to AR, and you keep adjoining it, and in the end you will just get a single element F gamma. So consider this field E, which is obtained by adjoining alpha and beta to F, and we want to replace this alpha and beta with a single element gamma. That's what we want to prove. So we want to make sure instead of alpha and beta you have single element gamma, and we have beta is separable over F, and alpha may or may not be separable. So first we start with minimal polynomial. So minimal polynomial for this element alpha is F. Minimal polynomial for beta is G over F. And say you have other roots also, alpha 1, alpha 2 all the way to alpha s. These are roots of F. So they are S roots, and you set the first root as alpha. So the first root A1 is alpha, and these are roots over some field K over E. So beta is already separable, so we are not talking about any extra field here in beta. So this beta you set as equal to B1, and then B1, B2, B3, B4 all the way to BT be the roots of G. So beta is one of the roots, and there are a total of T roots, and you are saying B1 is beta. So now just let us focus on the first root, alpha and beta. So just let us focus on this, and then we will take care of the rest of the roots. So you set this element gamma as equal to alpha plus C beta, and then in the end we want this gamma here instead of alpha comma beta. And this C is an element of the field F, so the underlying field F. So then we have these polynomials G of x. This G of x would lie in F of gamma x. So to F you have adjoined gamma. So G of x was already a polynomial over F. So if you adjoin gamma to it, it will still be a polynomial here. The coefficients will still lie in a larger field because they lie in a smaller field. And F of x already lied in this capital F. So f is also a polynomial over f. So now you have introduced a gamma here. So once you introduce gamma, it may no longer be polynomial over f, but now you have a joint gamma here. So this is also polynomial over this. So now you put beta, so g of beta is 0 because beta is a root of g. So g is the minimal polynomial corresponding to beta, and we have already set beta is equal to b1 here. So this is a 0. On the other hand, if you put beta here, you get gamma minus c beta, and you know this gamma minus c beta you can see from here is alpha. So this thing is equal to alpha from this equation. So this is equal to f of alpha. So alpha is the root of f. You can see the correspondence here, and alpha is equal to a1 here. So this is 0. So you can see that beta is a root of g of x and a root of f of gamma minus c of x. So beta is a common root for two polynomials. Now we can adjust c. So this we will do later. So we adjust c so that beta is the only common root. So this is our claim, that beta is the only common root, so that greatest common divisor of g of x to f of gamma minus c of x is x minus beta. So we haven't proven this yet, but we are saying that we are going to adjust c so that this holds. So that is, we only worry about the first two roots, alpha and beta here. So we have to adjust c so that these other roots do not cause a problem. They do not come out as common roots. Now if this holds, so suppose our claim holds, greatest common divisor of g of x and f of gamma minus c of x is precisely x minus beta, then we use the following fact. So greatest common divisor of two polynomials has coefficients in the same field. So g of x and f of gamma minus cx, g of x and this, they have coefficients in the field f of gamma. So therefore this fact says that greatest common divisor will also have coefficients. So it also has coefficients in the field f of gamma, or you can say this is a polynomial in the field this. So in particular, notice that beta is a constant here. So that implies that beta lies in f of gamma because it's a coefficient, so therefore it lies here. Now this implies alpha, which is equal to gamma minus c beta, also lies in f of gamma. So gamma already lies in f of gamma. C is an element of f, so therefore it lies here. Beta we have already shown that it lies in f of gamma. So alpha also lies in f of gamma. So this implies that f of alpha beta, you join alpha and beta to it, you still get f of gamma because alpha and beta both are generated by this. So both of them you can see lie here. So this is the end of the proof. But now we have to just prove this claim. So we want the greatest common divisor to be x minus beta. So our party can be spoiled by these other roots. And the way to avoid these other roots getting in here is to adjust c. So how did we generate gamma? So gamma was alpha plus c beta. So instead of c, now we write some variable x here. So the problem can come if our gamma here, this gamma becomes equal to some other roots, you know, ai plus x bj. So notice that we could have the same situation here. We could have, say, g of some root bj. This will be 0. And if you correspondingly plug here, you will get f of gamma minus c of bj. Now we do not want this to be equal to 0, because if this is equal to 0, then you will have another common root which is bj. So we do not want this to be equal to 0. So this cannot be equal to 0 only when, you know, this is not equal to some f of ai, because the roots of f are these ai's where I goes from 1 to s. So we do not want them to be any of these roots. So we do not want this gamma minus c bj be equal to this. So prevent this at all costs. Gamma minus c bj should not be equal to ai. So to do this, we will adjust this c. So we want to avoid these roots a2 to as and b2 to bt, because we are only worried about the first roots. So therefore we solve these equations. So you know this I will go from 2 to s and j will go from 2 to t. So j goes from 2 to t and I goes from 2 to s. So not the first one, because alpha and beta we obviously want to hold. So you solve this equation, you get x is equal to ai minus alpha over beta minus bj. So you only have finite number of values here, which you can plug in for x. So this x is what is going to be c. So since these are finite roots here, you have finitely many solutions. So you have finitely many x's to solve. Now for any of those x's, you will have this equality hold. So you choose a c which is different from all these solutions, all these finite number of values. Therefore you will never have the condition this, because you have chosen c so carefully that it is not the solution of these equations. And that's the end of the story. So therefore you will have only one common solution. So notice that this is a very constructive proof. In the start you could have just started with just two roots, so one root for f and one root for g, and then try to solve this over, and then made sure that other roots do not show in by using this construction. So this is a very constructive proof.